Good morning. How are you doing? I am Mr. Ish. Thank you for joining me for this video. We're talking about here a very mandatory pre-calculus topic, but it plays very well into integral calculus. We are looking here at partial fractions decomposition in a relatively short video, but this will not be it because I have comprehensive video or videos on the way with regards to this. Why are we talking about this? Because there are integrals out there, rational functions, which require you to utilize this technique in terms of their integration. But I don't want to talk any more about integrals or calculus. We're focusing here on the technique of partial fractions decomposition. I have a very comprehensive video on the way. Let this be an overview of partial fractions decomposition via 3 examples that we will look at. I will try to present these from a relatively easy to a hard one, and if supposedly this represents a rational function for us. What does decomposition mean? You have a certain rational function which is made up of parts. If you were to combine those parts, add them up, you would end up back over here. Go about doing this. Well, you want to utilize this technique ideally for those situations here where the highest order of exponents, you see you have a polynomial in the numerator and in the denominator. The denominator must carry the higher order of exponents with regards to the rational function. Here you have a power of 1, here you have a power of 2, so this has a higher order, and this is ideally suited for this technique. Factor this out. You have x plus 2, x minus 1. The number of factors will generally tell you the number of partial fractions which were involved. When you added them up, you ended up back over here. You ignore this for a while. You have 2 factors here. You look them at in terms of adding them up. 2 individual fractions which will add up to give you that. One keeps one of the factors, the other one retains the other factor. You see, x plus 2, x minus 1. What you have to do is here find a common denominator, but do not combine the common denominator. Keep everything as is and do a fraction over here. A goes in this common denominator these many times, so you'll do a times x minus 1. Remember, complicated partial fractions decomposition will require matrix algebra techniques. This goes in that, x plus 2 times all of this with regards to only the numerator is equal to what you have right here on the top, x. And you can add placeholder values like 0x squared plus 0, all of these placeholders which are meaningless, but you can add them in if you want. The most difficult part of partial fractions decomposition is this right here, because once you've determined the number of factors, there are a variety of combinations which come into play which help you demonstrate and develop this. This right here, this template as you want to call it, is the most difficult process. You open this numerator up over here. You have ax minus a plus bx plus 2b is equal to everything after that equal sign, x plus 0. You know the highest order I'm looking here is to the power of 1, therefore I have to the power of 1. But I do have some sort of constants coming into play right here, constants without variables, hence I'm putting a 0 placeholder. Combine these in terms of the like terms. The like terms are ax, bx, which are the variable terms, and you have constant terms. Combine them into separate linear equations. I have an ax plus bx is equal to, which very well fits with this, x. Then I have the constant terms minus a plus 2b is equal to 0. Remember, partial fractions decomposition is a series of techniques, procedures, which varies based on the type of rational function you have. It is only experience and practice which helps you negotiate and navigate through these type of questions. Get rid of the variables over here. You're really looking at something which is a plus b is equal to 1. I'm converting these into systems of linear equations. I have minus a plus 2b is equal to 0. I have to solve for a, I have to solve for b, and that right there will give me my partial fractions. What do I have over here? I have minus a plus 2b is equal to 0. You can do substitution, elimination, matrix algebra, whatever you want, you can do that. If I take this a on the other side, I have 2b is equal to a, or wherever I have a, I have 2b. I have an a over here, I can put 2b here. 2b plus b is equal to 1, and then you know here b is equal to 1 over 3. So we've determined b. We put b over here, 1 over 3, and then we can very well easily determine a from here. If b is equal to 1 over 3, a is equal to 2 times 1 over 3, which is 2 over 3. That right there is what I wanted, because this right here is going to fall right into here and give me my partial fractions. A is 2 over 3, just plug it in right here. You can write your answer in multiple ways. Let me put them here. 2 over 3 over x plus 2 plus b is a 1 over 3 over x minus 1, or you can write it in a better way. And let's write it in a better way, but let's come down right over here and I erase all of this, and then we write the decomposed partial fraction. It'll be 2 over 3 into x plus 2 plus 1 over 3 into x minus 1. That right there is my decomposed partial fraction of this rational function, and you've seen the procedure before you. You can see it's rather complex, elaborate process, but that's how it is. You could have multiple ways in your head and into how you will do it. This is how I've learned to do it, and this is how I do it. So let me show you two other questions. Okay, let's look at this question number 2. We have x minus 1 divided by x squared plus x4. We see here again the denominator has the higher order exponent, so it's ideally suited for partial fractions decomposition. Again, once you've identified you want to use that technique, take your expression and simplify the denominator in terms of factoring it. You'll have x squared into 1 plus x squared. Right there, there it is. You have to find all the varieties of combinations of factors from there. I have an ability to do something else over here. I can do x times 1 plus x squared. You see how x squared has been split into that? The number of factors I have over there will determine the number of items I'll have here. A plus b, right? I have one here, but you have to use the highest order of those combinations. If one is an x, I really have an x squared. I'm not going to put an x here because this represents one combination, x squared represents another combination, and the third combination is 1 plus x squared. 1 plus x squared is an irreducible factor. You cannot do anything more with it. It's an irreducible factor. At any point you have an irreducible factor here, a linear irreducible factor, which means you cannot factor it further. You must bring an expression on the top, not a single item like here we have. The expression must be utilizing the next letter but with a variable. Cx plus d. Again, time, practice, experience will tell you and explain to you and help you in determining these. This right here is the hardest part. This template again is the hardest part in terms of this entire procedure. Common denominator here is x squared times 1 plus x squared. Now you must determine how each letter goes into this, or how many times the numerator goes in there. A has a denominator x, it goes in here. A times x squared plus 1 times. Alright? B, this goes in all of this denominator 1 plus x squared times, right? 1 plus x squared times. And then you have cx plus d. All of this goes in this x squared times. Now you must open this and we must equal it to what we have right here with the placement of factors, the zero factors to help fill the placeholders. Open this up carefully. You'll have ax cubed plus ax. You can't do a silly mistake here, otherwise everything will be wrong. Plus bx squared plus cx cubed plus dx squared is equal to this item here, x minus 1. But you see I'm having cubes here, so I'll put 0x cubed. You see I have a square item here, so I'll put a 0x squared, but then I have also a plus x minus 1. You see I've gotten all the placeholder values, cubes, squares, ones, and constants, to cover up everything here. Now you must isolate the common terms. You have cubed terms, and the cubed terms are a plus c. You look at the coefficient of the common terms. A plus c is equal to this cubed term 0. That's your one linear equation. Now look at your square terms, b plus d. These are your square terms, right? B plus d is equal to this square term, which is a 0, right? Yes, you have 4 linear equations forming here, but solving them won't be hard. You have your single variable term ax is equal to x, or a is equal to 1, right? Just looking only at the coefficient of this single variable x. Now look at your constant terms. You have a b and you have a minus 1. B is equal to minus 1. You see we have 4 linear terms, equations, but they're easy. We already know what a and b are. If b is equal to minus 1, d here must be equal to 1. If a is equal to 1, c here must be equal to what? Minus 1. You can write your entire values here as this: 1 comma minus 1 comma minus 1 comma 1. All you have to do is now plug a, b, c, d into this template right here, and let's do it. And let's, you know what, plug the template values right over here. I know a is a 1, so I'll make this 1 over x. I know b is a minus 1, I can make this minus 1. You can convert this into a minus, or you can just keep the minus right over here. I know c is a minus 1, which will become a minus 1x, which is just a minus x. I know d is a 1, and here it is. This right here is your decomposed partial fractions of that rational function. If you add these, you'll end up here, and that answer should be good. Again, remember, here you had this combination of terms come out. you always have to utilize the highest combination. One is the x, but then you have to use the x squared. And then anytime you have an irreducible linear factor, it's irreducible, you have to bring in an expression here on the top like I had, cx plus d. Alright, if you had a reducible linear factor, which means it could be factored out more, then you have to factor out more, and then you would end up with more template length over here. Alright, let's look at one more question. We'll do this next question is a bit of a trick question if you don't use common sense, and it is also a very easy question if you do common sense. We'll do it in both ways, because the non-common sense way gives you practice and the common sense way gives you a tip which you need to utilize. Okay, last question. This can be done in two ways, as I was alluding to, the common sense approach or the non-common sense approach. And I don't mean to insult anyone by saying that. I'm just trying to stress the point that you should always utilize this tip, where when you are having a rational function, you simplify it first. You have x plus 1 over x squared into x plus 1. Okay, you have a common factor here which cancels out. You end up having 1 over x squared, and this right here is your decomposed partial fraction of this. That right there is a very quick way. If you have to integrate this, you know it's hard, but if you have to integrate this, you know it's not hard at all. It's a polynomial. Bring this up, x to the minus 2, and you integrate that and you're done. But anyhow, if you didn't recognize this need to simplify a rational function, then you will go down the long route. The long route will be this. From here, you're doing your template determination. Your template determination again will be this. You're looking at all the varieties of factors. This x squared would generate an x, and then you have an x plus 1. You'll have 3 items. 3 factors, 3 items. One of those items here is a over x, but the other one must be b over x squared. You must utilize the highest version of that one, right? If this is an x, you must utilize x squared. But here you don't have an irreducible linear factor, you have a reduced linear factor, so you can just put a c over here, x plus 1. It's no longer further factorable, therefore you're not thinking about a non-reducible or irreducible linear factor. It's something which is already reduced. You bring a single item on top, and you now look for the common denominator, which here is x squared times x plus 1. Anyhow, this goes in that these many times. X plus 1 times, b goes in here, x plus 1 times, and then of course c goes in here, x squared times. If we do this entire lengthy procedure, we should still end up with that, and we will. Open up everything, you'll have ax squared plus ax plus bx plus b plus cx squared should equal all of this. Everything always equals, right, your original numerator. But I'm seeing square components here, so I add a placeholder, 0x squared plus x plus 1. Now I combine the like terms. I have the square components. I have an ax squared plus cx squared, but I'm only looking at their coefficients. A plus c is equal to this 0. Then I'm looking at your single variable or your linear variable components. A plus b is equal to this, which is 1 in terms of coefficient, and lastly b, your constant, is equal to that constant, right? B is equal to 1. If b is equal to 1 and you have this expression here, then a must therefore be equal to what? 0, right? B is equal to 1, a plus 1 equals 1, a is equal to 0. If a is equal to 0, c therefore must be equal to 0. In terms of your final answers, you're looking at 0, 1, 0. But these are the items you can very well plug right in here. When I plug them right in here, a is a 0, right? When I plug b over here, it's a 1, right? 1 over x squared, it makes sense, it should be a 1. And then c is a 0 right here. You're zeroing out everything, you're basically left with only this, and that right there is right. And you are indeed verifying it to be true. Remember, again, with partial fractions decomposition, this template which I formed at the very beginning of this question is the hardest part of this question, because it requires you to look at all the combinations of these factors which come out. Those combinations will dictate the number of items you have, and it will in part dictate what type of letters you put. Sometimes they're just linear or constant. Sometimes you have to put an expression here based on the presence of a non-reducible linear factor. Like if you had something like this in the denominator, x squared plus 4, you can't factor it out anymore. On top of this, you would put something like cx plus d. If you had something like this in the denominator, you know you don't put something here because it's factorable. You would have to factor this out further into x minus 2 into x plus 2, so that when you were to separate them out, you'd have a single letter here, whatever that single letter might be. Over non-reducible linear factors, you put a combination of expression. Over reduced factors or reducible linear factors, you put single letters. Alright, and that drives the procedure. Anyhow, I have a comprehensive video or two coming out in the near future. This is just an introduction to this entire technique. Thank you for watching. Have a nice day.